Hello everyone. So today's lesson is all about altitudes. So to begin with, we should talk about what an altitude is. I know I've said it in class before, but it's good to have precise definitions. So given any triangle, the line drawn from one of the vertices that is perpendicular to the opposite side or the continuation of that side is called the altitude. And the side that the altitude intersects would be called the base. So that's just a fancy word. So let's see. Perpendicular means forming 90-degree angle. So just imagine you start at one of the vertices, like in triangle GHI. Let's start at G and just drop the perpendicular down like that to the point J. Now you have your altitude. And your altitude is almost, the same, it is the same thing as your height. Just a fancier word, altitude. And that means that HI is your base. Now, we could have drawn an altitude from I to HG, which would be somewhere around there. That would also be considered an altitude as well. Because again, it's just whatever line that's drawn from a vertice to an opposite side that makes a 90-degree angle. Now, in the case of a right triangle, it's since you're going from the vertice to another side at a 90-degree angle, your altitude or height would just be whatever this side is. And that means your base would be located right there. So right triangles are probably the easiest to identify, but you shouldn't get so worked up about the differences on what the altitude and the bases are and stuff like that. For example, if I can actually, let's see. Let's get rid of some of this stuff, and I'm going to show you why you shouldn't get so hung up on which is which. Now, let's say we take this triangle here, the right triangle, and we were to rotate it. I'm going to rotate it 90 degrees. So now we have that same triangle, just rotated so that the side BC is now where AB was. And I'll even hide the original right triangle. And now we can see that even though we have the same triangle we were just working with, now the side CB is the altitude. And that AB would be the base. This is different from how we had it in the original triangle in the first place. So in the original triangle, let's see. Can I even show it now? Probably not. Yeah, in the original right triangle, well, let's just make it again real quick. What am I doing? So that would have been this one. Now, even though they have the same dimensions, we said that AB was the altitude and BC was the base. But now, if we just think of it in a different way, we could have said CB was the altitude and AB was the base. Again, it really doesn't matter too much as long as you understand the height or the altitude is forming a 90-degree angle with the side it's intersecting. So let's continue in the case of an obtuse triangle, which is the one we have right here. So, let's say I wanted to make the altitude from point D. Well, if I draw the perpendicular, it's not going to hit that side FE. That's why in our definition, we use the word the side or continuation of that side. Continuation means if I extended it, so now I'm going to make a line out of FE, and then I were to draw the perpendicular from D, making that 90-degree angle, that would be my altitude. So this line right here, dA, is my altitude. Because it's hitting the continuation of the side. But that original side, FE, is still considered the base. So that's probably the weirder case. But again, it's not really too crazy. Just think, I always use the saying it's just measuring from the top of the triangle to the bottom. And the top and the bottom are all just relative to how you position them in the first place. So, with that being said, let's learn about one of the first properties of altitudes. Prove that the lines, problem 7.22, prove that the lines containing the altitudes of a triangle are concurrent, meaning they meet at the same point. So we should think back, and remember we can draw altitudes at each of the vertices. So each triangle technically has 3 altitudes. We want to show that those 3 altitudes are all going to meet at a common point. Now let's start with some generic triangle ABC. So I'm just going to make a triangle. It's going to, what the heck? Alright, generic triangle with my polygon tool. So something like this. Very simple looking. Now I need to show the altitudes all meet at the same point, or prove that it always will. Now how should I go about doing that? Well, by definition, all of the altitudes have to be perpendicular to their base. What does that remind me of? Well, perpendicular to the base, perpendicular lines, well, we just learned about perpendicular bisectors. And one of the things that we proved about perpendicular bisectors back last week was that the perpendicular bisectors of the sides of a triangle are concurrent. So this is almost what we want to prove. We have shown that there are perpendicular lines that are always concurrent in a triangle. But this is perpendicular bisector, and I want altitudes. So what I need to do is show that there is some relation between altitudes and perpendicular bisectors. Remember, bisector means to cut in half. So how can I do that? Well, we also learned about something just yesterday in the medians lesson. We learned about something called the medial triangle. And the medial triangle is when we connect the midpoints together to form another triangle. So, for example, in this diagram, DEF is connected from the midpoints of AC, AB, and CB, and it creates this medial triangle. That means I have this midpoint here, and if I draw a perpendicular line through that midpoint, it would be also the perpendicular bisector. Now, what do I know about these medial triangles? Why should I be thinking about them? Well, it's because we also proved all these theorems about them. That they have parallel lines, and they're congruent with each other, and so on and so on. So, if I were to, I need to basically prove that the altitudes of a triangle can form together to make the perpendicular bisectors of another triangle. And by doing that, I need to prove that this triangle ABC is the medial triangle of some other triangle out there. So, what I want to do is think, medial triangles have these properties. Most importantly, the thing that probably interests me the most is these facts, that these lines are parallel, that DF is parallel to AC, and EF is parallel to CB. Maybe that gives me an idea on how to start the construction of this medial triangle. So, what I'm going to do is draw some parallel lines. Now, I'm going to draw the line parallel to AB at the point C. That would be right there, and parallel like that. And then I'm going to draw the parallel lines for the rest of the sides. So I want the parallel line through A parallel to BC, and I want the parallel line through B parallel to AC. And now I got this nice diagram going on here. And I can label these intersection points. So I'll label that D and E and F. So those are the intersections. Now my job is to prove that ABC is in fact the medial triangle of DEF. Now, how can I do that? Well, parallel lines always imply congruent angles. So, let's note that if AB is parallel to EF, then that means we have that this angle here is going to be the same thing as this angle right here, because they are alternate interior angles. And likewise, this angle here must be congruent to this angle here. Same reasoning, alternate interior. Because BC is parallel to DE. So we have shown that the angle EAC is congruent to the angle ACB. And we have also shown that the angle ACE is congruent to the angle CAB. Well, why is that so important? Well, because according to this midline theorem, the medial triangle, has all these properties, that the triangles are congruent with each other. So if I can show that that medial triangle, that triangle we're working with, ABC, is congruent to the rest of the triangles, then that will show that it's the medial triangle. Well, how can I seem to be having some sort of congruence between ABC and AEC. Well, how can I prove it? Well, they both share the side AC. And that implies we have angle-side angle similarity. So, I know that triangle A, B, C is congruent to triangle, and that would be ABC, so CEA. By angle side angle congruence. So, if these two triangles are the same, then that means this length here is going to match up. Well, it matches up with AC, so that's kind of silly. But the parallel line AB, so this length here, matches up perfectly with this length here. Awesome. So, where can we go from there? Now, I'm not going to write out all the steps because if you can show this, it should be fairly easy to show all the other triangles are congruent too. Because, for example, we have, you know, if BC is parallel to DE, then that means that this angle right here if BA is parallel to EF, that implies this angle with the two tick marks is the same as this one because alternate interior angles. That's interesting. And I know this angle is the same as the angle here. BCA is the same as CBF. Again, parallel lines, alternate interior. DF is parallel with AC. So, and I have that this side here is the same. So again, I can show that triangle ABC is congruent to triangle A to B to C. Well, that means this angle is the one tick mark, so AB, so FCB. Again, angle side angle. And it doesn't take much to show the rest that this triangle here, well, this angle is the same as BAC. And this angle has to be the one with two tick marks, and eventually you'll get triangle ABC is congruent with triangle AB, so BAD. Wonderful. Now let's start to clear up the diagram a little bit. Don't need this. Don't need this. Alright, now I need to show that now that I have all these triangle congruences, well, what does that show me? Well, I showed that EC is the two tick mark side because it corresponds with AB. Now, in triangle BCF, I look and I have that CF is the side that contains the angle with two tick marks and the angle with no tick marks. Well, on ABC, that is the side AB, the no tick mark angle and the two tick mark angle. So CF has to have the same length if they're congruent. And if this is true, then that means that point C cuts off EF in half. So this is proving that C is the midpoint of EF. Because since CE is equal to CF, C is the midpoint of EF. Again, because it's just splitting it in half. And the same logic can be used with the rest of the sides. So, for example, this angle at E has to be the three tick mark one since they all add up to 180. So that means that AE is between the 1 tick mark and the 3 tick, or the, sorry, not 3 tick marks, 2 tick marks. What am I doing? Is between the 1 tick mark and the 2 tick mark angle. So the 1 tick mark angle and the 2 tick mark angle is BC on the triangle ABC. So that means that this side has 3 tick marks. And if I look at DA, then this angle has to be the 1 tick mark 1, and we get the same thing, that this has to be the 3 tick mark side, which means that A is the midpoint of DE. Now I'm not going to write the whole reasoning out because we're just using the same logic we used here. So now I know A is the midpoint. And the same thing can be used to show for B. So the side on ABC between the 1 tick mark and the no tick mark is the single tick mark AC. That means this has 1 and this is 1, so B is the midpoint as well. So we have shown that B, A, and C are the midpoints of their respective sides. A is the midpoint of DE, B is the midpoint of DF, and C is the midpoint of EF. So all that is implying that by definition, if we look at it, it has to be the ABC has to be the medial triangle, because we are connecting the midpoints to the opposite vertices of the No, we are not doing that. We are what we are doing is connecting the midpoints to each other. So we have connected in our previous diagram all the midpoints of DEF to make another triangle ABC. So ABC is the medial triangle of DEF. Wonderful. So I'm going to clear up the diagram because there's a lot going on. So let's just get some of the stuff out of the way. Now that we've already proven everything we need to know. Alright, let's get all this out of the way. Sorry, this take forever. The software isn't amazing, but it'll do. Alright, so all that logic has shown that we have proven triangle ABC is the medial triangle of triangle DEF. Now, why was I trying to show that again? Well, I'm trying to show that all the altitudes are concurrent. And I can do that by drawing the perpendicular bisectors of DEF. Because what's going to happen once you see how I'm going to draw it is we're going to take our perpendicular bisector tool and draw the perpendicular bisector of of DE. And notice that this perpendicular bisector of DE passes through A. And because of that, and because of the fact that it's perpendicular, it makes this 90-degree angle DE. But DE and BC are parallel, which means that corresponding angles are the same. So that means this angle is also 90 degrees. So that means the same perpendicular bisector of DE is the altitude from A to BC. And if we draw the rest of the perpendicular lines, or perpendicular bisectors, I should say, we get the one going through B, and then finally we get the one going through C. And they all have that same property, that they all are the altitudes of their respective sides. And therefore, they are all meeting at this point here. So if I were to continue labeling these points, we would say that BG is an altitude, AH is an altitude, and CI is an altitude. So, because ABC is the medial triangle, we have that AH, BG, and CI are the altitudes of A, B, C, triangle ABC. However, the line AH, and the line BG and the line CI are the perpendicular bisectors of triangle DEF. And since we have already proven in the past that the perpendicular bisectors are concurrent, they all meet at a point, and the fact that the altitudes are contained within these lines, thus we have since perpendicular bisectors are concurrent, the altitudes of triangle ABC are also concurrent. And that completes the proof. Because the altitudes of ABC are the same thing as the perpendicular bisectors of DEF, and we know that the perpendicular bisectors are concurrent from a previous proof, that implies, since the altitudes are the perpendicular bisectors of another triangle, that the altitudes must also be concurrent, specifically the lines containing the altitudes. And that completes our proof and gives us the first important property, which is that the altitudes of any triangle are concurrent at a point called the orthocenter. Orthocenter. And we usually denote this with the letter H. So our first really new definition, the orthocenter, the point where the altitudes are concurrent.